Boom! All right, let's get after it. Good morning or afternoon, physics class. All right, y'all. Downward launched objects, the throwdown. Time for the throwdown. Don't video this, it might get us in trouble because we're going to be throwing down. All right. How do downward launched objects fall? Well, you did W30B. And so you kind of did this already. Let's just formalize it here in the notes a bit, set you up for a more advanced version of it, W34. All right, reminder. This unit is about projectiles for the most part, and it is only a projectile when it is under the influence of gravity only. So when you throw something down, yes, something has to throw it, but the problem does not include the hand throwing. Remember we put the soft brackets? Nor does it include the ground hitting. In fact, we put those parentheses rather than the square brackets because the problem exists between these moments but does not include them. So, not when the hand is touching the object, not when it's hitting the ground, but everywhere in between. It is only under the influence of gravity, we'll call it a projectile. All right, so once the projectile is released, now it's subject to the same gravity as a drop or any sort of throw, and so it experiences the same acceleration. What is the acceleration of a downward thrown projectile once it has been released? So this comment right here, once it has been released, is redundant. As soon as we say the word projectile, we know that as long as we're near Earth, the acceleration is a very special acceleration that we call a g. And it is, of course, 9.81 meters per second squared downward toward Earth's center. Sometimes people call that negative, sometimes not. But either way, it's down toward Earth's center. All right, so we're going to sketch this business. Now, these are just the velocity graph, these are just the vector graphs. Velocity is one of the vector graphs. Acceleration and displacement are the other two that we're worried about. So these are just the vector graphs. We are to choose a direction to be positive. Assert this yourself. Graphs in general, test makers prefer up to be positive, so no real sense in fighting that. Now you see these dotted lines here. These dotted lines represent a dropped object. And we talked about this a bit in W30B, so this should be a bit familiar to you. So for the dropped object, the acceleration, since up is positive, was a negative 9.81 meters per second squared. The initial velocity, that's the boundary condition now, the initial velocity is 0. The final velocity was something greater than 0 in the downward or negative direction. The slope of this line was exactly, since slope of Vt is a, the slope was exactly negative 9.81 meters per second squared. And the displacement started at 0, just as you see here, and it increased in the downward, or what we would call negative direction for this problem. In fact, the slope of the displacement graph matches our velocity graph. So at the beginning, the slope is 0, just as the velocity is. As the velocity grows in the negative, the slope grows negatively. So these all fit. Here, the velocity, the slope is acceleration. You see that slope stays constant, just like the acceleration was constant, both at negative 9.81. Slope over here goes from 0 to something bigger, all in the negatives. Fine. Now let's talk about the throwdown. In a throwdown, like we said up here, once the object is released, it is a projectile, which means 9.81 meters per second squared acceleration. So come on over here and mark that in the same exact spot. That's the same, negative 9.81. That did not change. Now that tells you the slope of the velocity graph also has to be exactly negative 9.81 meters per second squared. However, the initial velocity is different. The initial velocity is downward. We call up positive, so it must be somewhere over here like negative, and it is parallel to that earlier graph, and it too has a slope of exactly negative 9.81. Well, would you look at that? Good. Okay. Finally, the displacement graph at a sketch would look a lot like this. However, notice the slope of the displacement graph is velocity. The velocity starts at, they didn't give a number here, but some negative number, which means the slope over here has to start at some negative number. So you're going to start out with some steepness to begin with, and then of course that steepness continues to grow. Not a great drawing, but there we go. Okay? Good, there are your graphs. The blinking light diagram, just as a reminder, a drop problem. They started out close, then got a little farther, then a little farther, then got a little farther, then a little farther. The throwdown starts out also close, but their first close is already farther because it's already going faster. So the throwdown problem is just like the drop. The acceleration is downward acceleration, also downward velocities. However, the acceleration, they're both the same, but the velocities are not. So here the velocity is perhaps the vector represented by that length, whereas this one is represented by a greater length. Okay? So it's like an advanced version. Same with this displacement graph. It's an advanced version of the drop problem, meaning advanced in time. All right, check this out. A ball is thrown downward from a roof at 30 meters per second. Okay, before you get crazy and start thinking, oh, I got you. The VI is 0. Well, let's call up positive for this one also. Even though when you do your calculations, I recommend calling down positive. What's the ball's instant velocity? Well, don't come running over here getting all excited about, the velocity at 0 is 0. Well, no, it's not a drop problem. The velocity at 0 is whatever it's thrown at initially. And since up is positive, this is a negative 30 meters per second. Remember the meaning of acceleration. It's how much the velocity changes each second. So after 1 second, the velocity will have changed by 9.81 meters per second squared downward. So our negative 30 just became negative 39.81 meters per second. Another second after that, the velocity will have changed by another negative 9.81 or 9.81 downward. So now we will be at, remember in the drop problem is 19.62. Here though, here we are starting with a head start of 30. So we're not at 19.62, we're 30 ahead of that. We're at negative 49.62. And finally at 3 seconds, in the drop problem, we went another 9.81, which got us to 29.43. But in this one, we got a head start of 30 meters per second downward. So negative 29.43 is actually negative 59.43 meters per second. Fine. The whole point of this little chart here, this question, recognize that whether it's a drop or whether it's a throwdown, one may have a head start. Throwdown has a head start, but they still change by 9.81 down each second. That is inalienable. As long as you're near Earth and it's a projectile, meaning the air doesn't have much impact, boom, that's it. Then, of course, we have the half-second intervals. Not essential that you know these, but just for completeness and thinking about it, If it's going up 9.81 each second, then each half second it's doing half that. So we'll be at negative 34.91 meters per second. At 1.5 seconds, we'll be about 15 faster than we started. Remember, this was approximately 10, so really 30, 40, 50, 60. Here it's going to be 35. This is going to be 45. Really negative 44.72 meters per second. And finally, at 2.5 seconds, I was at 1.5. Use that little subscript. And the velocity at 2.5 seconds is roughly 25 meters per second downward, more than it started. But that works out to, what's that? Negative 54.53 meters per second. Okay? Good. And for those of you who like those approximations, this one was exactly negative 30. This one was about negative 35. This one's about negative 40. We go out over it. 3 seconds later, it'll be 10, 20, 30 downward compared to how it started. It already was 30 downward, so this one's about negative 60. This one's negative 50. These approximations aren't bad. Negative 45 and negative 55. Okay. Recommendation. As you're calculating, as you'll see in question 26, as you calculate a throwdown, I recommend, since the velocity is down and the acceleration is down and the displacement is down, I say call everything positive. I say choose down as positive for throwdowns. Let's check this problem out. A rock is thrown downward. Uh-oh. I say choose down as positive. You don't have to. I think it goes nice. Look at the other givens. From a height of 75 meters. Now we got to be careful with these heights. Start to watch out for those. Maybe that'll be the displacement, maybe not. With an initial velocity of 15 meters per second. That's definitely a given. What is the rock's speed? There's a given. As it reaches the ground. When you see reaches the ground, the height now became a proper given. Because that height matches the displacement. Of course, the displacement has direction. The height does not. Givens with units. Okay, so the height is the displacement. The displacement is downward. What we call down positive. So this is good. We got 75.0 meters downward, which is positive. This problem is happening near Earth. So you know the acceleration, which is downward, what we call downward positive, will just be 9.81 meters per second squared. Then we know the initial velocity, they told us. VI, they said is 15 meters per second. Now they said downward, and so this also is positive. See how nice it is? Everything's working out. By the way, you can assert your positives if you would like. You know, feel free to come in here and do something like this. This is positive. And this is positive. And this is positive. Okay, finally, what is the rock's speed? Vf. Now I'm going to pull one of those pause the video moments. So, yes, pause the video and determine what equation will allow you to solve for this set of givens. Go ahead, pause that. All right, if you're back, I hope you saw VF, VI, A, and D is the dang forgotten one. VF squared equals VI squared plus 2AD, which, by the way, you're more than welcome to write straight into it. VF squared, we'll square root both sides, equals VI squared plus 2AD. Notice, by the way, you'd have some issues with negatives in here if you weren't careful with your signs. Now, if you called up as positive, A would be negative 9.81, D would be negative 75, and this would come out as a positive. If you were not careful, you'd call A negative 9.81, D positive 75, and now we're going to have an issue because this will be a negative term with this positive term, and then you'll probably just pretend it's a positive result even though it's not, and yeah, then it just goes downhill from there. So run your numbers on this business, you'll be all right. W34 is the assignment based on this. You have that in your packet. Get her done.